Hello everyone. Today we're gonna talk about how large language models are trained, reinforcement learning basics, and some policy optimization algorithms. After watching this video, you should be familiar with pre-training, post-training, supervised fine-tuning, reinforcement learning with human feedback, PPO, DPO, GRPO. So there are so many things to cover, let's dive into it.
So let's start with modern LLM training. This graph shows the most typical modern LLM training pipeline. As you can see, it can roughly be categorized into two parts. The first one is pre-training and the second one is post-training, also referred to as fine-tuning. The most typical fine-tuning way right now is supervised fine-tuning plus reinforcement learning with human feedback. I'm going to cover it in later slides. The current LLM development trend is more focused on post-training instead of pre-training right now. So pre-training is the initial phase of training an LLM where the model is exposed to a massive dataset of text. The dataset is often unlabeled, and the text can come from books, articles, websites, etc. The goal is to equip the model with a broad foundational understanding of language, allowing it to learn linguistic patterns, structures, and semantics from vast amounts of unlabeled text data, so it can be better prepared for later specific tasks and reasoning. This is a graph that shows the goal of pre-training. My goal is next token, and then the model will predict prediction. The goal of it is to understand language in general and do well in next token prediction. Post-training is to refine and specialize the model's capabilities, making it more useful and aligned with specific tasks and human preferences, or even develop reasoning capabilities by techniques like instruction tuning and preference learnings. Up to recent, supervised fine-tuning and reinforcement learning from human feedback have been the dominant post-training methods for LLM. The assumption was human labeled data, for example, chain of thoughts, is necessary to teach structured learning. This assumption is currently being challenged by DeepSeek R1. Some of it we will cover it in this episode. The other we're going to cover in the next one. This is an example of what post-training is doing. We pass in answer yes or no, 2 plus 2 equals to 5, and the answer should be no. This is a math-specific task, and we want the model to be more capable in math and also show some reasoning capability in math deduction if possible. As I was mentioning, this is the most popular post-training framework from OpenAI. The first step is basically supervised fine-tuning. It's collecting demonstration data from human and train a supervised policy. First, what we need to do is to pull a prompt in the prompt dataset. In this case, the prompt is explain the moon landing to a 6-year-old. And then after we have the prompt, some human, the laborer, should demonstrate the desired output behavior. This human will answer this prompt, and this will be a labeled dataset. And we're going to use the data to fine-tune GPT with supervised learning. Step 2 is to train a reward model. We need to collect comparison data. How we do that is, given the prompt, we want to generate multiple model outputs. For example, we get 4 output A, B, C, D, and some of it is better than the other. The laborer, which is another human, will rank the output from best to worst. And after we have the comparison data, we pass it to the reward model to train it so the model knows our preference. And the step 3 is to optimize the policy against the reward model using reinforcement learning. I know there's a lot of new terminology, policy, reward, reinforcement learning. We're going to cover it later. So a new prompt is sampled from the dataset, different from the previous prompt. And then the policy generates an output. Basically, the model starts answering the prompt of write a story about frogs. And then the reward model trained from step 2 calculates a reward for the output, and then we use it to update the policy. Basically updates our LLM using PPO. I'm going to cover PPO later. So let's first talk about supervised fine-tuning. SFT is a technique where a pre-trained LLM is further trained on smaller, specifically labeled dataset to adapt its behavior and performance for a particular task or domain. So it's essentially customizing the model for a specific use case by providing it with targeted training data. SFT is actually not very different from pre-training. Both have next token prediction as their underlying training objective. The differences are following. The first one is the data for SFT is labeled. The SFT use labeled data where both the input and desired output are provided, so it allows the model to learn specific patterns and relationships. The second difference is task-specific adaptation. By fine-tuning with relevant data, the LLM can become better at tasks, like summarizing medical or legal or answer customer service questions, depending on the dataset used. So this is an example of supervised fine-tuning. There will be a human laborer putting all the response for a prompt. So the first prompt is asking to write a poem, and then the second one is to want the human to roast the model. In both cases, human put those answers in to train the model. Okay, so let's talk about reinforcement learning to understand the whole picture. So RL is a type of machine learning where an agent/policy learns to make decisions by interacting with an environment, receiving rewards for positive actions and penalties for negative actions, essentially learning through trial and error to maximize its cumulative reward over time, mimicking how humans learn from experience and feedback in the real world. This is different from learning from labeled data in traditional supervised machine learning, and this is particularly useful for situations where the optimal action is not explicitly defined and requires exploration to discover the best strategy. First keyword is policy. Policy is a rule used by agents to decide what actions to take. It can be a neural network, it can be not a neural network. So it is common for the words agent and policy to be used interchangeably. It can be a little confusing since now we're in agentic era, supposedly. Agent, policy, or in this case, you can think about it's the model that we're training. It's supposed to take some action and it's going to interact with the environment, and then the environment is going to give a reward to the model itself, and the model is going to be on a specific state. So this is the relationship between agent, environment, action, state, and reward. The action is a stochastic distribution of the state. And then a state is a complete description of the world on which decisions are made. All the information that you care of the environment should be captured in the state here. In the Flappy Bird example, in order to play this game, you only need the horizontal distance and vertical distance to optimize your action. So in this case, vertical distance, horizontal distance is your state. And the environment is there's an obstacle. So reward is the goal of the agent, and it's to maximize the total rewards collected. Reward can be different for different tasks. In this game's case, reward is the score of the game. Value is the total expected rewards if you start in a state or a state action pair and then act according to a particular policy. So in this case, this is a chess game, and this is basically the state of the current chess. And the value V given state S for white is high, white is in advantage. So the move knight to d5 is the previous state and had a high value. So value is the expected discounted rewards over all trajectory sampled from a policy. So this is the value given the state, and then this is the expectation of the reward discounted given the state. I'm going to explain reward discounted in the next slide. So discounted rewards are a way of measuring how much an agent values future rewards compared to immediate rewards. Discount factor is a critical factor in determining how well the agents learn. In RL, an agent learns by taking actions in an environment and receiving rewards. The agent's goal is to maximize the sum of all the rewards it receives over time. The discount factor is a value between 0 and 1 that determines how much the agent values future rewards. So if this value equals to 0, that means the agent only cares about the first reward it receives. And if this value is 1, then it means the agent cares about all the future rewards equally. So the discount factor is very important. The choice of the discount factor can significantly affect the agent's learning performance, on finding a balance between exploration and exploitation. The next keyword is trajectory. It means a sequence of state and actions in the world. So trajectories can be discrete or continuous, as you can see in this graph. This is the categories of RL algorithm. There's model-free, model-based, and there's many algorithms down here. Today I'm going to talk about policy gradients and PPO. And I'm going to talk about DPO and GRPO, which is not here, but it all belongs to the policy optimization. Let's talk about policy gradients first. This part is very math heavy. If you can't follow all the mathematics, don't worry about it. This should not affect your ability to practically try out reinforcement learning. We want to maximize the total reward over sample trajectories from a parameterized policy network, as depicted in this formula. We can do so by gradient ascent. If you're familiar with machine learning, you should be familiar with gradient descent. Gradient ascent is basically the same concept, it's just minimizing, maximizing. You can consider this gradient descent, it's the same. So the gradient term in the above equation is the policy gradient right here. So the probability of the trajectory coming from a given policy is this formula right here. And then if you want the derivative of this, you need to use the log derivative trick, and then you can get the derivative of this probability. And then after you do a derivative, since the initial state rewards and state transition don't have the policy network parameters, so you can just cross those out. You just have this formula left. Since this is an expectation right here, it means that we can estimate it with the sample mean. This is the sampling formula, where D is the sample set trajectories and D absolute is the number of trajectories. It basically means we have a formula here and we want to use gradient ascent or descent to find the global optima. And in order to do that, we can get a sampling function to get that result. The next one I want to talk about is PPO, proximal policy optimization. This is the graph of how PPO workflow looks like. So in this graph, you can see there's a policy model. This is basically the LLM we're training to generate better content. And we have a value model right here. It's a critic. It's another AI model that acts like a critic. It estimates how good each state is. This helps PPO make smarter updates. So as you can see, policy model and value model, both of them needs to be trained. And the reward model here is the AI judge that scores text based on human preferences. This one is a frozen model. We're not updating it. Same with the reference model here. It's a baseline or frozen copy of the initial language model, helping to ensure the fine-tuned model stays reasonably aligned and does not deviate too much during training. This one is often the supervised fine-tuning model. And there's the KL regularization. This one is to prevent a new model from deviating too drastically from previously established model by penalizing large differences between their probability distribution measured by the KL divergence. So the steps of training is pretty complex. The first step is the policy. The model creates a bunch of text samples from different prompts. The second step is reward model scores each text sample. Third step is calculate advantage using GAE, which is generalized advantage estimation. So this is a typo. This is giving reward. So if you give reward after whole sentence is complete in a text generation task, it's high variance and low bias. So you can only know the total reward after everything is done. But if you give reward after each token is generated, then it's low variance, high bias. Because with local optima, you never know what is the final reward. The last token can be totally out of place. So GAE balance between the above two. So it balances between variance and bias. The fourth step is to update policy to maximize the PPO objective function. The objective function contains volumes. The first one, it encourages higher rewards because that's our goal. And then it limits policy changes. And then it also encouraged the LLM to be more exploratory by adding a entropy bonus. And then we update the value, which is the critic, to be more accurate in predicting goodness of different text generations. So this is basically how PPO works. Again, I'm going to flash this workflow. Policy model, bunch of generated outputs. It goes to reference model, reward model, computes the KL divergence, and then it gets the rewards, and then the value model is going to get the value, and based on the reward and value, we're going to compare the GAE and get the advantage. So the advantage is basically value minus rewards. And then this advantage is going to send to the policy model to update the policy. And then the value model is also going to take the GAE weights to update its ability to better judge what is good and what is bad. So the next one I want to talk about GRPO, which is Group Relative Policy Optimization. This one is what DeepSeek R1 is using, so I'm going to talk more in the next episode. This is the comparison between two different workflows. As you can see, PPO, it requires to train two models. One policy model, which is what we want to use eventually. The second one is the value model, which is a critic that tells us what is good and what is bad. It is very complex, it is very expensive. The PPO requires this training model to estimate the average reward given a state, and it's later used to compute the advantage here. The advantage is basically reward minus the value. GRPO is trying to avoid training two models by using a group sampling to estimate the average reward. This, in practice, the sampling pool size in their paper is around 60. So in this case, they are able to avoid training a second value model in a very smart way. This is what makes GRPO more efficient and less complex from a system standpoint. Let's now talk about direct preference optimization, DPO. DPO also is motivated by the complexity of PPO. So remember, the complexity for PPO actually lies in several points. First, you need to train a reward model. Then you need to use the reward model to train your policy. And during you train the policy, you still need to train a critic, a value model. There are many complexity and computation needed for PPO. So DPO wants to do something different. It directly optimizes the model's parameter based on human preferences. It bypasses the traditional two-steps process of training a reward model and then use the reward model to train the policy. And in that policy training, you still have to train a critic model. So DPO starts with human preference data. It's basically pairs of responses with labels indicating which response is preferred. And then this is the smart part. It's using a special cross-entropy loss function that directly compares the logits from two models. First, it feeds both the preferred response and the dispreferred response to the trained model, and it gets the logits for both. And then it do the same and pass a preferred response and dispreferred response to the reference model. So this is a frozen older version of LLM, often can be the SFT, and then it gets the logits for both. Afterwards, they calculate the cross-entropy loss function with above logits. This is basically the math formula. It's also very long, but you can see the goal is to increase likelihood of the preference response and decrease likelihood of the dispreferred response. We have talked about PPO, GRPO, and DPO. We already know from a system and computation perspective, PPO is the most complex. GRPO improves the system complexity and computation by removing the critic model training. DPO simplifies it even further, removes the need for training a reward model completely. But it's really hard to say at this point which algorithm is better, which one is the go-to method. In different situations, different algorithm might perform better. So from my knowledge, PPO is usually more stable and sometimes perform better than DPO. And currently GRPO is only used by DeepSeek, so it still needs time to shine. So right now, it's very hard to say which one is the go-to. So keep up an open mind of PPO, DPO, and GRPO. So why use RL in post-training? This is a good question, right? Why not just do supervised fine-tuning? Why use RL in post-training? Supervised data can be insufficient in the first place. SFT is not enough. And also, if you want to train a really smart AI, you're going to face complex and dynamic environments. Fine-tuning with RL is particularly useful when a task or environment involves complex interaction, where traditional SFT struggles and is less efficient. Also, RL fine-tunes allows models to adapt to different tasks, user preference, and environment without massive retraining efforts. Also, RL takes into negative feedback and allows online learning. Finally, I want to use a concrete post-training end-to-end example to end this episode. First one is supervised fine-tuning of LLM. In this case, our pre-trained LLM is GPT-3, and then we have human-labeled SFT data. For example, the prompt is what is RL, and the human answered RL is blah blah blah. And then we use this fine-tuned data set to do supervised fine-tuning, and then we get the SFT version of LLM. The next step is to train the reward model from human feedback. As we mentioned, we want to sample some prompts, and in this case, the prompt is explain SFT in 80 words. And then we use the SFT LM, the previously trained version, to generate multiple outputs. And some is good, some is bad. So the human is going to help us to get ratings and ranking. In this case, the first SFT is A, blah, blah, is the best response. And then well SFT is also the second one. And then the worst response is about dogs. And then after we get the ratings and rankings, we use the reward model objective listed right here to train the reward model. Third step is to use the reward model to train our LLM, to optimize the LLM. So in this case, we need a new prompt, and then the RL prompts right now is summarize DeepSeek's advantage. And then the reference model is SFT version of LLM, and then this is the policy that we want to train. The policies model is going to return DeepSeek is, and then we use the reward model to show the rewards. And then we also combine the reference model's outputs and use this RL objective, which contains raw reward, and then the KL penalization, and then the original pre-training data gradients to get the new gradient. And this combination here is using the PPO RL algorithm to update the RL tuned LLM, which is the policy. So this is a very concrete example of how post-training works in each step. So hopefully with this episode, you already understand how modern RLM are trained, including pre-training and post-training. And then you should already understand the details within pre-training and post-training. As a side effect, you should also understand how reinforcement learning works and also the policy optimization algorithm. Thank you everyone. If you like my video, please subscribe, comment, or like. See you in the next episode.